So, dear all, it's great to having you here on this EURASIP webinar about recent developments in network information hiding. This webinar is in the organization of Technical Area Committee of EURASIP about biometrics, data forensic and security. And our presenter will be Steffen Wendzel. I will say first some words about the TAC committee and then about our guest lecturer. So this TAC focuses on multimedia security, on data forensics, watermarking, covert communication, applied cryptography, biometric recognition and forensics, video surveillance, network security, physical security, data privacy, and similar. We are 21 members and 2 associate members from 12 countries. And one of our members, Steffen Wendzel, will be lecturer today. So I will say a little bit about Steffen. He is my dear colleague. We collaborate a lot on different things. Steffen Wendzel is a professor of information security and computer networks at Hochschule Worms, where he is also the scientific director of the Center for Technology and Transfer. In addition, he is a lecturer at the University of Hagen. Before his professorship, he was a postdoc at Fraunhofer FKIE in Bonn, where he led a research team on smart building security. He received his PhD and his habilitation from the Faculty of Mathematics and Computer Science at the University of Hagen in 2013 and 2020, respectively. So, dear Steffen, the floor is yours.
Thank you very much.
I forgot, sorry, to tell something. This webinar is going to be recorded, and also if you have any question, you can write in question and answer part, or you can raise a hand at the end that you can ask the question directly. Sorry.
All right, thank you very much, Alexandra, for introducing me. And yeah, as mentioned, we have a lot of joint work going on since several years. Okay, and today actually some of that will also be covered in the talk. I hope you can hear me well and that my video is stable. So the idea of today's talk is essentially to summarize some research work on information hiding in network environments that we did in the recent years. And I will start with some introduction. But before that, I want to quote Knut, Donald Knut. I think I don't need to introduce him because he's so famous. And so 22 years ago, he wrote, in my own field, for example, it was once possible for a grad student to learn just about everything there was to know about computer science. And nowadays, the subject is just pretty big, and it's difficult to cover more than a tiny portion of it. And I think that's true and was true already back then. I will come back to that quote in a few slides, and then I tell you why. So first, what is information hiding? Here are 2 different examples with some figures that probably everybody knows. I took them from Wikipedia. So one example is digital image steganography, where you hide some image or text or some kind of data in an image. So for instance, I hope you can see my mouse. The image of the cat is hidden in the image of the tree here. Another example is watermarking. And we find watermarks in analog and also digital formats. So information hiding is not always about hiding. Sometimes it's also about watermarking something, be it robust or not. But in the focus today is more the hiding component. And that discipline started quite early. So we know that in ancient Greece, people already applied simple forms of information hiding, or in that case, steganography. And that went on through the ages. And in the 20th century, these approaches became digital. So people started to hide data in text of image files, of text files, HTML files, and crypto protocols, network protocols, in file systems, videos, audios, images, and so on. And also in IoT environments. I added some, and recently in machine learning models, I added the red ones. They are not part of the original figure from that book. And I think this will go on. Some novel ideas will pop up in the future as well. And in contrast to the early approaches, where you had to give the secret message to some person, and that person transports that message, like let's say it's written on in form of a letter, and you hand the letter to that person, and you send, hey, let's please bring that letter to some destination, and that's quite slow, because it might take days to reach the destination, and the response is most likely equally slow. So what we have today with communication networks is that we have, in most cases, we have a constant flow of data, and also a pretty quick response time. So we can hide a lot of data in little time usually. Now, there are a few related disciplines like censorship circumvention, traffic flow watermarking, side channels, but they all share some common ground. And while some are more about changing the characteristics of some traffic, so for instance, let Tor traffic appear as Skype traffic, others are more about tagging some flow so that you can link flows, or hide the sheer fact that the communication is taking place. Typically, people would say, well, if you want to do censorship circumvention, or if you want to bypass some filter, why don't you just use Tor? Well, it's because Tor is subject to attacks since years, and so with methods like website fingerprinting, you can still identify some information or a little bit of what's going on Tor. And this is why people started to encapsulate Tor into a third-party traffic obfuscation system. This is done in many different ways. So one is Stegotoro. So you take the Tor traffic, you put it in that system, it modifies the traffic so that it looks different than Tor, and then you extract that Tor traffic again at the receiver side and get the secret information. So that's the idea of most of these tools. And what they do is they try to let the traffic just appear as some legitimate traffic. So that means just not Tor traffic. And one simple example that is already 11 years old is Peekaboo. So what they did is they adjusted the sizes of network packets so that it does not, I think the idea was not to look like Tor, but I'm not 100% sure anymore. But the idea is that you just add padding bits or bytes to the packets so that you change the original packet's size. Obviously, you can also do this with the timing of packets and with lots of content that you let appear in a different way. Most of these approaches are essentially the same. So you have some model that somehow has some attributes indicated by the star, and some recipient of the information that is observable. For instance, in wildlife, this could be a prey-predator scenario. Let's say this is a deer and this is, I don't know, a tiger, or a wolf is probably the better example. And sometimes in nature, you have a mimic that tries to mimic the model. an insect that looks like a leaf, so that it's not easily discoverable by a predator. And so the recipient tries to identify the plus, because the mimic is never perfect. And in that case, what most systems for censorship circumvention that enhance Tor, etc., try to do is to perform a more or less perfect mimic of legitimate communication. And this is also done in steganography. And what we discussed essentially last year is that there are a lot of reinventions happening, scientific reinventions. And that means that we have redundancies in research, because censorship circumventions, steganography, covert channel research, traffic type obfuscation research, and so on, they overlap. They have different terms, but their ideas are similar. And these commonalities that can be found in these domains should be somehow unified, so that scientific redundancies are minimized. Now, back to Knut's words. If we go further in time and add 22 years in that case, so we land in 2023, then we can just replace my own field with network concealment research and say, well, it's the same. Well, Knut didn't say that, but it's still true. The field is so enormous that it's difficult to keep track of what's going on in even related domains. And for this reason, we looked at all the methods we could find in the domain. So we scanned hundreds of papers, read how they implement hiding, concealment, and so on methods to get an overview and to see what terms are used and by which community and so on. And the first attempt here was done in 2013 from our side. Was a small group of 4 people, which led to one paper that proposed the first taxonomy based on so-called patterns, hiding patterns. So we came up with abstract descriptions of what is actually done by hiding, concealment methods, and so on. And this was unified and extended and also enhanced over the years. So new patterns emerged in that book here, and the taxonomy was refined, and then again refined. And the blue dots here represent papers that introduce new patterns. I think Alexandra Velinov is also here, and this is a paper led by Alexandra Mileva. Laura Hartmann is one of my PhD students. So more and more patterns arose, or here's one a paper by the University of Magdeburg group who applied the taxonomy to ICS steganography. And these developments led to a revision of the original taxonomy in 2021, more patterns, then a taxonomy for just indirect covert channels and side channels, published last year at Asia CCS. And the current state of the taxonomy is this one. It's still a preprint. It's under review since July last year. And this is a project where several authors are involved from several institutions, where we revised the whole taxonomy again and made it backward compatible till the very first one. And this is not just for network steganography, it's essentially for all domains, but I will give you examples for that later. Here's a list of the involved or participating institutions and the names. Not so easy to read, I guess, but yeah, some of them I already mentioned. And the first taxonomy looked like this. So it was just 11 patterns, but we could already describe 109 hiding methods of the research literature with these 11 patterns. So the gray boxes are the patterns, and they can have subpatterns, as you can see here. So, and the core idea is you either modify the, no, sorry, I just want to click on these elements to point you to what I look, but obviously it changes the slides then. So you can modulate the timing behavior or the storage, the stored data of, for instance, network traffic. And then you can modify headers or padding or payload. And sometimes you modify the structure of a packet, like packet size adjustments, or you drop packets, something like that, or you preserve the structure and just like modify values. The taxonomy developed further. This is, I think, this is the last version of the taxonomy for network steganography. So as you can see, more and more patterns emerged. I wrote down the core publications that enhanced this taxonomy on the left side. And the question you might ask is, how does such a pattern look like? So here's an example pattern. It's a old one. So the idea was already published in the 1980s, I think by Gerling and Wolf. And the core idea is, if you send network packets, then you modulate the size of the gap, the time gap between the packets. So it can be small or big gap. And if you have two symbols, then obviously you can transfer 1 bit per inter-packet delay or inter-packet gap. And you can do this for whatever kind of packets you want to transfer. I wrote down Ethernet and IP packets, but obviously that in the end, it doesn't matter which kind of packet or frame structure you have. And you enhance this description with lots of additional details, like an implementational description, literature references, aliases, and so on. But I come back to that a little bit later. However, we will take this pattern as an example through the whole class seminar. I will come back to that pattern a few more times today. As mentioned, the early approach was network specific. And we wanted to unify the terminology and taxonomy for the whole steganography and network concealment and so on domains. And this is why we came up with a preprint called a generic taxonomy for steganography methods. It will be essentially one for concealment methods, etc. as well, but we will rename that most likely. But that's not so easy, because if you want to create a taxonomy, and many taxonomies are created every day and published in tons of papers, you should consider a few problems. First problem, different names for the same thing. So you need to unify the terminology in a way that you incorporate the terms used by all the different outroggers and all the different subgroups in the community. And this is what was also done, at least partially, in biology. So the most famous and the dominant taxonomy in biology comes from this guy who's from Sweden, Carl Linnaeus, and he published in the, I think, 18th century, the taxonomy for the living things that is still used today. So what we can do in computer science is to use aliases in, for instance, a pattern language such as PAL-MAL. For instance, if we modulate packet sizes, then in the literature we find terms such as size, covert channel packet length, covert channel filed length, padding size, or padding covert channel, and so on. It's just a few examples here. And with aliases, we can at least say, okay, they all belong to the same pattern. And the second problem is, who cares about yet another taxonomy? As mentioned, there are so many taxonomies that are published. several of them get very few or no citations because they are not bringing any benefit and people are not involved. And so the idea is to involve the community. So for instance, let's say you've discovered a new pattern. That's great, contact us, we will integrate it in the taxonomy, we have an official website, we will reference your publication, your code, and so on. And you are the inventor of that pattern. You published some work that matches some pattern. Great as well. We are happy to reference your work in that pattern, or your code, your evaluation, and so on. So you get some visibility because we integrate your work, we cite your work on the website and in publications, or you plan to contribute something fundamental, then contact us. Well, at least once it's through review, we will be able to extend it. At the moment, it's a bit of a locked state because we wait for the review process to finish. Problem number 3. Yes, there are a couple of more problems to come. People need to understand the taxonomy. And one reason why the taxonomy that we have today in biology is so successful is because it's easy to use. It's a binomial nomenclature. And for instance, if you have the gray wolf, then it would be called Canis lupus in that taxonomy. And I think my audio just off. Just one. Okay, so it should be there again. So that, and if you want to be more precise in the sense of you have some subcategory of that pattern, of that category, let's call it a category, then you just add terms like dingo for the Australian dingo. And we did something similar here. So we also have essentially binomial nomenclature. So we have states or values that would be what is the object that we focus on, and then we have a word that describes what we do with it. For instance, we perform some kind of modulation. And if we want to be more precise, then we could say, well, it could be this least significant bit modulation of the state or value, or it could be in a network context. So we add another word and another layer for the enumeration. Okay, so this works, and we checked whether we can apply this taxonomy to the works that we know in network steganography, in file system, text, CPS, and image stego or digital media stego, and so far it works. You always have to check that every idea fits in one category and that every technique, so every technique must be categorizable, but only in one category. And that means that taxonomies should be exhaustive and mutually exclusive. And this is so far the case because we abstracted from the context. So let's say you have network, text, or CPS steganography. What is it? What kind of steganography do you apply if you perform some character case modulation in CPS configuration data, like for instance, the TIA portal for ICS environments? Well, in our understanding, it doesn't matter. It would obviously be text stego, but also somehow CPS stego or text stego applied to CPS. Now, let's say you transfer this over the CPS network. What is it then? Well, it also doesn't matter because it never matters in our taxonomy, but it would be text steganography applied somehow to network traffic that is residing in a CPS environment, I guess, and belongs to and describes CPS configuration data. But this is complicated to explain, and people probably have different views on that. So we say, okay, it doesn't matter. Then we came up with some object-oriented approach that became too complicated and led into problems. So what we have now is a very simple, keep it simple and stupid approach. We have elements, and elements can have states or values, and they can have sub-elements. And then again, these can have states and values and sub-elements. That's a little bit abstract. Here's an example. So for instance, in network steganography, an element could be a network packet, a header field, a packet size property, or the time of occurrence property of a packet, while the value would be the actual packet size itself, or a sequence number value for TCP, or the actual time value for the time property, and so on. In file systems, this could be files, inodes, and so on. I won't go through the whole table here. It's in the preprint. Just for the network example, if you have a flow, then the flow is an element, and the flow contains sub-elements like packets. And these packets, these packets contain fields that are storage values, like this IP version 4 header here. But the flow also has a duration and a number of packets, overall number of packets that are virtual attributes. So they are also elements. And a packet contains these different header elements, and they might contain more elements and so on. And a packet might occur at some certain point in time, things like that. So this is how we compose structures in an object-oriented way that is also highly flexible. I will give you a few examples for different domains in a moment, but first, there are more problems. Problem number 5. Some patterns are hybrid ones. For instance, the sender does something different than the receiver to send or receive the secret information. One example would be the artificial reconnections pattern, where here a sender would trigger reconnections of some smartphones that are in some Wi-Fi, and the receiver monitors these smartphones connections. So the action performed by the sender is different one than for the receiver. It would be the same operation if the receiver just writes some bits in a packet header, and receiver would just read the exact same values again. Then we would consider this as not a hybrid one. But here we have a hybrid setup, and we can describe this with the new taxonomy because we allow hybrid definitions. So embedding and extraction process are decoupled. We can describe them separately. This is joined to what I just said. Actually, I mixed things up. So for the hybrid ones, we have 2 operations performed by the sender, and for the embedding versus extraction approach, we decouple the extraction and embedding process in the sense that both can have different patterns. For instance, if the sender relocates a virtual machine, then it performs some commands. So we write some storage values, and then we transfer a virtual machine, let's say from Asia to Europe, and the receiver measures the round trip time, and that would be a different pattern. So the location of the virtual machine indicates the secret information, and this is then represented by the time behavior of how long a response takes for the receiver's connection. Now, the generic taxonomy that we came up with is also quite simple. So we have these embedding patterns that describe how the information is embedded by the sender, and then we derive representation patterns or extraction patterns that describe how the receiver extracts the secret information. Essentially, they are the same. It's just that in one case you write, in the other case you read data, or you wait some time, and in the other case you measure some time gap or something. But the core ideas are the same, so we can derive the representation from the embedding patterns. And we came up with 2 major patterns. We either modulate a value or state, or we somehow influence the occurrence of an element. Like a network packet, we could, for instance, send 10 or just one network packet. That would be element enumeration, or we could position an element in time, send a packet at a specific time of the day, or modify the gaps between packets. And for the value modulation, we would override reserved, random, LSB values with other ones, add some redundancy, or perform character state value modulation. Now, I will give you examples for different domains now, just to show or to exemplify that how this taxonomy can be applied to network steganography, but also to very different domains. So first example is for network steganography, and it would be network element enumeration. Here in that case, we would encode the secret signal by mimicking TCP retransmissions. And because we send multiple segments, multiple instances of the same segment to simulate a retransmission, it would be a network element enumeration because of these duplicates. Another example for CPS steganography would be to encode some secret signal by influencing the response time of a CPS actuator. And that will also be element positioning just for CPS, because we position the actuator action in time. Or file system steganography. So let's say we have an unused block in the file system, we place some data there, then it's our state value modulation, because we modulate the state or value. That state or value is reserved or unused, and it belongs to a file system. So the pattern is file system reserved unused state value modulation. And all these ZAP patterns are derived from the bigger ones. So if you look at file systems, you just check what is done in the network or digital media context for reserved unused state value modulation, and you get their ideas as well. So we link the different domains together. Text steganography. Let's assume we modify some features of characters in text, like underlining, font type, or color. Then that would be text character state value modulation. So again, state or value modulation of a character and its text stego. That's the context. Or digital media steganography. So there's still work to be done. It's the initial subtaxonomy. And let's say we insert a blue screen or blue pixel at some location in a video or image file. And so if we position that element, then it would be a digital media element positioning, because we modulate the position of the element, the blue screen or pixel, in a temporal or spatial way. And here the more complex methods are still like described in the infancy in our taxonomy. So there's still a lot to do. And what we also can do is side channel considerations. So we can, if we take, for instance, a network side channel where an attacker scans a target and sends a username and a password, and sends this combination many, many times, like done in a work by Sebastian Schinzel several years ago, then let's say this is some system, some website where you can log in. So you enter username and password, and obviously if in case the username exists, the password also needs to be checked whether it matches. So you usually send them a hash, and then the hash needs to be checked whether it's correct. But that consumes additional computation time. So the response time is slightly longer if the username exists than if it does not exist. So if you probe the same username many times and then another username many times and so on, and you measure very, very exactly the response time, then you can infer information about whether the user might exist on the system or not. And this would be network element positioning, because the response, although unintentional, so it's a passive covert channel or a side channel, which is the same, would be network element positioning, because the target positions unintentionally the network packet in time. Traffic obfuscation does also work. So the example that I've shown you with the packet padding is network element enumeration, because we add more bytes, padding bytes. So we enumerate the padding bytes in this sense. And yeah, so that these examples, I think, show that the taxonomy is quite nicely applicable to several domains. But you might ask, where do all the problems go? So that this is problem 7. So we try to have a one-size-fits-all solution, but obviously we sacrifice detail in the patterns, on the patterns level. And this is why we have a multi-stage approach. So we have the generic taxonomy. We derive domain-specific ones, for instance, for network steganography. And then we have a unified description method using the patterns with a unified structure, so that experimental replications are easier, because they all, the unified description method asks you to describe certain things of your hiding or circumvention method. And if you apply this one, this description method, then the comparability of the research is given more easy, is given. And we came up with this unified description method in 2016 because we did a survey and checked the papers in the domain and checked what do they describe. So for instance, do they describe an application scenario or not? And as you can see from this, I think 131 papers, well, slightly more than 100 have at least a partial description, but what are the required properties of that communication channel? What are countermeasures, or what is the channel capacity, bandwidth or something? So it goes down already a lot. Or robustness. Robustness is described only by few papers. Some cover a control protocol, but this is reasonable because often you do not have an internal control protocol. And our description method unifies that, says, hey, you should write something down for this aspect, this aspect, this aspect, and then you are fine and your research is replicable. Problem number 8. It's a second last problem, so stay with me. Will people really use the taxonomy the right way, or will they misuse it? Well, we came up with design rules, and if the people follow these rules, things should work fine. But therefore, they really have to read the paper's details. I won't bore you with the design rules. Problem 9, is it backwards compatible? Yes. So in the preprint, you will find tables that explain you how the previous patterns match and can be transferred into the current taxonomy, into the generic one. So yes, it's backward compatible. And there's also taxonomy for side channels done by my former PhD student, Tobias Schmidbauer. It's mostly his work. And so for an indirect covert channel and sometimes side channel, you have some intermediate node that you exploit in some way, so that the covert receiver can infer the information that is located at an intermediate node. Sometimes the information is redirected. Sometimes it's that you manipulate some node and monitor the node, and sometimes that's called the dead drop pattern. You can store information in network caches like the ARP cache or the NTP cache. We have papers on these dead drop approaches. So we created papers on that. But if you want to look into the details of these patterns and several examples, they are all listed in this publication. Okay. So what else can be done with such a taxonomy? So first of all, we can evaluate what's new. Is an idea already there, or is it entirely new? We check the patterns of the taxonomy. Is there something that is already matching our idea, or is it really new? That helps the community. We can categorize and describe what is already there, and that's also helpful. And we can identify gaps, so we can say, okay, there's something missing. For instance, using the unified description method, we can say, well, they described a detection approach, but no limitation or prevention approach for some hiding techniques. So that's a research gap that could be addressed. Now, let's pick a sample pattern, and as proposed or as mentioned, we will use again this interpacket times or element positioning pattern where we modify interpacket gaps. I will briefly introduce two detection approaches. Classical approaches by Kabuk et al. So the first one is the epsilon similarity. You record the flows inter-packet gaps. So let's say for these 600 packets, you measure the inter-packet gap or inter-arrival times. Then you sort them and you calculate the relative differences. They are called lambda values. And then you calculate the percentage of lambda values of a given flow that is below some threshold called epsilon. This is why it's called epsilon similarity. And the second one is essentially an entropy-based approach. So again, we record a flow or a window of the flow, let's say 600 or maybe 2000 packets. We record the inter-packet gaps, the deltas here. We round them and perform some string coding of the inter-packet gaps. The leading characters represent the zeros behind the comma, and then we compress this string and we calculate some kappa value, which is the length of the original string divided by the compressed string length. And the idea here is that because we round the values, and the covert channel usually has, let's say, two symbols that occur many, many times, the string will be very well compressible for covert channel traffic. So you have the chance to have different kappa values for covert data transmissions. Then what we did is we wanted to replicate experiments using these approaches. And we came up with Vodikov, which is the Worms distributed covert channel detection framework. And we can configure, generate traffic here, but we can also take captures, extract metadata, run this into some detection modules. They run in parallel, and the results are then stored on a distributed file system, and we can visualize the results. And there's a follow-up project called Vodikov Plus, which will be funded starting in January, where we will continue developing this system. And we ran several evaluations for the compressibility score, for instance, that you can see here. So legitimate traffic is the green one, and then we have different covert channel types in red and blue. And for instance, we replicated the approach with different rounding precisions. And as you can see, that already influences the compressibility score a lot, but also how well you can differentiate between covert channel and legitimate traffic and how much you have overlaps. And then we changed the media, because this was also not done in research so far. So how do the kappa scores differ if you have a high-speed Ethernet or a remote connection? And as you can see, they differ quite a lot. And then we tried different compressors. So we took Goethe's Faust, which is a famous German novel, and we compressed it with GZIP, with BZIP2, with ZIP. And we compared the results with the original results from Kabuk. And our results differed quite a bit. And this was also just interesting to understand how different are the results and for which configuration. So the tau value is, in this case, a configuration parameter for the covert channel. Essentially, it's the interpacket gap in seconds for the 0-bit, and the 1-bit signal would be 2 tau. Turned out Ethernet is very different in terms of the minimum transmitted interpacket gap, and this influences these kappa values a lot. And so we came up with something new. We thought, and that was just published this year, it's still early access. Because we thought, well, the epsilon similarity and the compressibility score, these papers are cited more than 1,000 times. And we wanted to see whether we can construct a covert channel with a good performance that can circumvent these methods, but in a way that that we would circumvent a sensor. And this is what we did. So if you look at the blue line here, it shows you legitimate traffic. And for a window of 2,000 packets, it's the sorted inter-arrival time, so inter-packet gaps. So typical legitimate traffic looks like the blue line, and some simple trivial covert channel looks like the orange one here. So we have 2 states and more or less the same value across many, many times. What we did is we implemented essentially the green one because we want to attack the 2 ideas of the epsilon similarity and the compressibility score. So the compressibility score performs well if the same values occur many times. So we introduced this slight slope here. So we have many different values that will decrease the compressibility score. So it looks more like legitimate traffic, and that can already circumvent the compressibility score. But how can we at the same time circumvent the epsilon similarity detection approach? Well, we introduced these steps here because then we have created lambda values for the given epsilon thresholds, so that we influence the number of lambda values in a sense that it matches approximately what is usually found in legitimate traffic. And it turns out, if you look at the compressibility score here at the bottom, so the original approach works extremely good. So this is using a mixture of lots of legitimate and covert traffic, and the detectability is extremely good. So AUC is 1. And if we use the same setting, but with the epsilon kappa Libur, so the approach is called epsilon kappa Libur because of the epsilon and kappa values, and because of the Excalibur sword. So we can reduce the AUC quite a bit. In that case, it will not matter whether it's 0.4 or 0.6, but it's decreased. This is again a mixture of all the traffic. There are many, many more plots and tables for the detailed configurations in the paper. For the epsilon similarity, it's similar. So for the original covert channel, all the different combinations mixed, we get a very good area under curve. I think this is 50% legitimate traffic here in each case. And for epsilon kappa Libur, it's again around 0.5, so we were satisfied. I've shown you a few different tau values here, just that you see it's not always the same result here. So the configuration matters, but also the mixture of so how many steps do we have and how is the slope. Okay, so because the reviewer said, well, that's nice. You have two major detection heuristics that you defeated, but what about current machine learning approaches? So we analyzed GAS. GAS was able or is able to detect also the sophisticated timing channels, not just the simple ones, really well. And we took their code, and as you can see, epsilon Kappa-Libur and a special variant called epsilon Kappa-Libur outlier reduced the area under curve quite a bit for at least the lab network configuration, but they also did some remote network connection settings. Here we could decrease the area under curve not so well, so from roughly 1.0 to roughly 0.9, at least 10%. And if the sample length is small, then it goes down even more. But the effect is not as big as in the previous case. And then we analyzed Snapchat. Snapchat is another approach that tries to detect also the sophisticated timing channels. And they transfer the interpacket times into an array, 2D array of pixels, and use image algorithms and features like mean gray value and so on to detect an image. And they were the only approach that could detect epsilon Kappa-Libur really nicely. So this is almost no difference here. The area under curve was about 1 in both cases. And we thought, what could we do to circumvent SnapCatch as well? Well, what they did is they map all the interpacket time values to a range of 0 to 255 because of the pixel values. And we just added outlier values to the covert channel so that the remaining values match the pixel value range of legitimate traffic. And this is what we call epsilon Kappa-Libur O for outlier, and got an AUC of 0.6. So that worked as well, but it would be easy to fix SnapCatch so that this would be detected as well, because you would just remove the outliers. Okay, so this is what I wanted to say about creating covert channels, especially for the purpose to circumvent specific countermeasures. Now, what else can we do with patterns? We can, or just started in September this month, to study attack attribution in a project led by the University of Magdeburg, and my group is also involved. And we study stego malware behavior and want to map the behavior to the hiding patterns and see whether specific stego malware of certain groups uses specific patterns. And my group is responsible for stego malware components that use internet standard protocols, TCP/IP protocol suite, DNS, HTTP, and so on. And there is a preliminary website. It's, I think, only in German for now. Well, project just started last month. And well, we will see how well this works. There's still a lot to do, but we hope that patterns help there as well. Okay, before I come to the end of my talk, I still have one more thing that I want to present you. It's also a novel thing. It's also still under review. It's also a preprint that is available since 2022. I think paper got in rebuttal at ACM-CCS, got rejected then, and now it's well, it's under review at the journal. And the idea is to have a new type of covert channels that we call history covert channels. This is like a fundamentally different type of covert channel. So what covert channels usually do is, and this is work with my 2 PhD students, Tobias Schmidbauer just finished, and my former advisor, Jörg Keller. And so the idea is that normally covert channels generate or modify some traffic that is just sent, and they hide the secret information in this covert channel or in these packets. So they either craft these packets or they modify them somehow. If they are sent by third party, they maybe perform some machine in the middle attack or something like that. We thought, what if we could just point to data that we've already seen? If we just say, hey, there was a packet, and this packet contains a secret message, matches, or that packet can represent a secret message that we just want to transfer, or we anticipate, we predict some future packets and send some tiny signal and say, hey, receiver, I think the next packet will match the secret message. Please interpret that packet. So how would this look like? And we call this a fully passive covert channel in context to a passive covert channel, because our data channel needs no sender, and the receiver is not necessarily the receiver of the covert message. So this is because we fully rely on third-party traffic. We just send a tiny signal, and the signal is much smaller than the secret message we transfer. How does this work? So the example I give here is dust. Did you see that, dust? And it works with the interpacket times pattern. So let's say we want to transfer the secret message M, that is 94D16 something. And over time, we observe certain packets. So first, we observe packet 1. And let's assume sender and receiver are in the same local area network, and these are all ARP broadcasts that can be observed. Now, the sender calculates a hash value of some of the packet's contents, and let's say plus a timestamp, and checks whether it matches the secret message. If it does not, then the packet is ignored. So we wait for the next packet. At some point in time, it arrives. Hash value is calculated. Is the hash value the secret message? No. Okay. And so on. Till, in this case, packet M arrives. We calculate the hash value. We usually just use the first 8 bits because otherwise matches are extremely rare. Calculate the hash value, see, oh, that hash value matches our secret message that we encrypted previously. And now we just sent a signaling packet, which is a legitimate ARP request that we would anyway send from time to time, let's say, just for the router's address in the local network that is sent from every now and then. And the receiver then just says, okay, receiver, you requested that address, or you send an ARP broadcast. That's enough for me. I will check packet M, because the receiver records these packets for some time. It caches these packets. And then the receiver says, okay, the hash value is the green one, and extracts it and has the secret message. That means that the receiver did neither send packet M nor modify that packet so that the secret message is embedded. It just points to that packet. And we have more variants of this in the pipeline. So the preprint here is from 2022, I think December. Yes, December. We have a new version that also works for remote connections. We have lots of additional experiments, but these are not published yet. So our evaluation, however, says, well, we cannot detect the channel because the compressibility scores overlap too much. And the problem is that we send so few signals that we just have no chance to detect them. And obviously, we cannot detect the data channel because the data channel is entirely 100% legitimate. We do not influence the transferred data at all, but these transferred data packets represent the secret message. In our local setup, it takes us 30 minutes to transfer a 8-bit chunk. And our remote scenario that is not published as a preprint, it's not part of that paper so far, it will be published soon. it takes 10 minutes. So and we did lots of recordings for like up to 56 days in different network environments, and we extracted the R packets there, and then we could calculate how long does it take till we find a match of the hash value of a packet. And because, well, you will say, well, devices always send the same R broadcasts, and that's true. There's just a small set per device of different addresses requested, so we add a timestamp to the calculation. We just concatenate the timestamp, and then we get a different hash each time. So this is the trick to get many different hash values. Good. What's the key message of my talk? And thanks for staying so long. So a large fraction of information hiding research, network, text, CPS, file systems, Stego, side channel research, traffic flow watermarking, traffic obfuscation, traffic morphing, censorship, circumvention, you name the terms, it overlaps. And we need to find common terms to prevent scientific reinventions and to speed up the developments of all fields jointly together. And one common taxonomy is hopefully a solution for that, or at least a contribution. That's my hope, and I think also the group's hope. So all the contributors, all the authors of that generic taxonomy. And some more takeaways are the following. So the new taxonomy allows categorizing methods of different domains, hopefully because you can never test all techniques for all domains, and some might just appear in the future and we cannot test them now. We have solved several problems like with the binomial nomenclature, we have the hybrid methods, we have design rules, and so on. We are capable of handling and categorizing new variants of covert channels like epsilon Kappa-Libor, which also belongs to the interpacket times pattern, and even a new class of covert channels, namely history covert channels with the dist implementation that also uses the same pattern. So we categorize this all in the same pattern. And if you look up the pattern, then you see all that information. That's the idea. And we have the multi-level approach. So we have the generic taxonomy, derived specific, domain-specific ones, and the unified description method to aid scientific replication studies. Right now, we finished more or less the generic taxonomy. It still needs to go through finalize the peer review. We have the indirect hiding patterns is already published. We extend the current taxonomy to other domains as well, and hopefully in 2 years have the generic taxonomy for Stego, circumvention, obfuscation, and so on. But it will be essentially the generic Stego taxonomy, just with the other domains included. So if you are interested, join us. Scan the QR code or visit the link. It's the same destination, I think. The other papers can be found on my website. And there's also stegopunk.net, a small website for of my group where also the patterns papers are listed. And yeah, with that, I conclude my talk. And thank you very much for staying the whole hour and for your attention. Thank you. And also thanks again to EURASIP for having me. It's a pleasure to be here.
Dear Steffen, thank you for
this. Okay, I think my audio doesn't work right now. Just 1 second. That's an issue on my phone because my audio receiver in the background always turns off and then stops working. I should hear you again now.
Okay, thank you very much for
this
nice talk.
Oh, sorry.
So there is one question from anonymous attendee here. Which network analyzer tool you suggest as secure to capture packets?
My audio is muted. I don't know why. So I hope it works now. Okay, it works. Sorry for the technical issues. After a few minutes, the Bluetooth device automatically disconnects and then it resets my audio settings.
Okay, Stefan, did you hear the question from attendee?
No, but I can hear you now, and I read
okay.
just one.
The question is, which network analyzer tool you suggest as secured to capture packets?
I'm not sure whether you mean. I'm not sure whether I get the question correctly because of the word secured, but I start with the first part. So a network, so we capture traffics usually in the PCAP format with TCP dump or Wireshark, and then we either put them in Vodikov, which is our own system, or Vodikov Plus, which will be publicly available to the community. And then you can run your algorithms, your detection algorithms on that. I also have a first proof of concept code. It's very early on GitHub on the StegoPunk website. There is a link to a GitHub repository. I think at the bottom of the site, if you click on the GitHub link, and there is a PCAP server. So it's a web server. You put the PCAP files in, and it extracts the meta information from the PCAPs, and then you have the meta information for your analysis as CSV. But you can simply also use T-Shark, for instance, to extract the data for the meta information, packet content data, like header field values are from the PCAP files. And then you usually run these data using some of your tools. So I wrote many of them in the last years, still in the shell under Linux. It's very old school, I know, but it works. And lots of my code is online. So if you want, you can recycle that code and can play around with that. I'm not sure whether I answered the question entirely because of the word secured. I'm still unsure, but if you want to add some follow-up question, just go for it, and I'm happy to answer.
Okay, if somebody wants, it can raise hands. Oh, thank you for answers. Answer is satisfied. Okay,
right.
If some of you have another question, it can also ask directly, or you can write in question and answer part. So, do you have some questions? Until we wait for the questions from other attendee, I would like to ask Stefan about, because we will be in the situation where we will have a new taxonomy which is generalized, and we have a lots of old taxonomies. So how to influence more to the researchers to use the new taxonomy instead of the old taxonomy?
That's not so easy to achieve. So my approach is to do something like this. So yeah. I reference the new taxonomy whenever I can. Yeah. Especially when it's already published, then it's, I think, easier. So for now, it's still a preprint. And we don't know whether the reviewers will say in the end, okay, yeah, we want you to change something. That would potentially be an issue for papers that still or that already used the new taxonomy. But yes, I think the new taxonomy is easier to understand. That makes it more attractive to the users, I think. And so it's really tailored for the community, and there's several open calls for participation. The group is much bigger now. As you know, we have people from several other institutions, so we can push this together, and we are no closed project. So we really are like a community project where we say, okay, who wants to participate, and we let people contribute and be part of it. So I hope this does two things. First, it should enhance the quality of the taxonomy, and secondly, it limits the barrier to use and join to use the taxonomy and to join the work group.
Okay, thank you, Stefan. We do not have any other question, so maybe we can finish here. Thank you for your lecture. It was very nice. Thank you for all the people attending at this webinar. So see you next time. Bye.
Thank you, Alexandra, for moderating the webinar. And yes, thanks again.
Thank you both.
Bye.
Have a nice day. Bye bye.
Have a nice day. Bye.
Bye bye. Thank you.
Bye bye.